99.9 repeating percent of mathematicians agree. 0.9 repeating equals 1. If because I said so works for you, you can go ahead and do something else now. Maybe you're like, 0.9 repeating equals 1? That's just 0.9 repeating-derful. Otherwise, on to reason number 2, or reason 1.9 repeating. See, it's weird because when we think of the number 1 or 2, in most contexts, we mean it as a natural number, like 1, 2, 3, 4, 5, in the sense that the next number after 1 is 2. 9.9 repeating may equal 10, but you wouldn't say you have 9.9 repeating lords a-leaping in the same way you wouldn't say you have 9.75 lords a-leaping plus a quarter lord a-leaping. Lords, leaping or otherwise, come in natural numbers. So what does this statement mean? 0.9 repeating is the same as 1? It looks pretty different. But it equals 1 in the same way that a half equals 0.5. They have the same value. You can philosophize over whether, if 1 is the loneliest number, 0.78 plus 0.22 is just as lonely, but there's no mathematical doubt that they have the same value. Just as 100 years of solitude is exactly as long as 10 plus 40 times 2 years of solitude, or 99.9 repeating years of solitude. So reason 2 is not a proof, but a reason to stay open-minded. Numbers that look different can have the same value. Another example of this is that in algebra, 0 equals negative 0. Reason 3. 0.9 repeating is a decimal number, a real number. See, if you want 0.9 repeating to be that number infinitesimally close to 1 but not 1, and let's face it, some of you do, then you're writing down the wrong number when you write 0.9 repeating. That number, infinitely close to 1 but less than 1, is a number, but it's not 0.9 repeating, or any real number. Okay, let's do a more 3.9 repeating mole proof for reason 3.9 repeating. According to this 3.9 repeating mula, 3.9 repeating is 4. First step, say 0.9 repeating equals x, then multiply each side by 10. Third, subtract 0.9 repeating from this side, which equals x, which we subtract from the other side. So 9.9 repeating minus 0.9 repeating is 9, and 10x minus x is 9x. Divide by 9, and you get 1 equals x, which you might notice also equals 0.9 repeating. There's no tricks here, it's simple multiplication, subtraction, and division by 9, which are all allowed because they are consistent. When something is inconsistent 9.9 repeating we just throw it out of algebra altogether. For example, in algebra, if you try to divide by 0, you get this problem where anything can equal anything. I mean, if you want to say everything is equal, fine, but your algebra sucks. Normal, everyday elementary algebra, the one they shove down students' throats as if it were the only algebra, doesn't allow dividing by 0, and so it stays consistent and suspiciously practical. We also could have shifted the decimal point twice, multiplying by 100, to prove that if you have 99.9 repeating bottles of beer on the wall, 99.9 repeating bottles of beer, take one down, pass it around, 99 bottles of beer on the wall. Alright, moving 3.9 repeating word. Reason number 5, there's infinite nines. If anyone ever thinks they have the biggest number, well, they don't, because just add 1 or multiply by 2 or whatever, and it's even bigger. Infinity, though, is not a number you can add 1 to get a bigger number. Adding 1 is an algebra thing that you do with real numbers. Subtracting doesn't work either. Infinity bottles of beer on the wall minus 1 is still infinity bottles of beer. When we did this decimal shift to multiply by 10, unlike uninfinitely many 9s, there's no last 9 that got shifted over to create a 0. Infinite 9s plus another 9 is still infinite 9s, the kind of infuriating property that makes infinity not a real number and makes that proof work. If you're the type of person who is discon 9.9 repeating with the idea that 9.9 repeating equals 10, you might also feel that 1 divided by 0 should be infinity. And, as it turns out, there's other systems of calculation besides elementary algebra where it does. That's right, mathematicians figured out how to divide by 0 a long time ago. But elementary algebra can't deal with infinity. If you allow infinity in your algebraizations, once again you get contradictions. Infinity may not be a real number, but it is a number, a hyper-real number. Hyperreals, like infinity and the infinitesimal, follow different rules, and while algebra can't handle them, some people thought they should be numbers, and you should be able to use them. And so they figured out how, and bam, you get something like calculus. Reason 6. Take the number 1 and subtract 0.9 repeating. It's pretty clear that it's infinite zeros, but you might be tempted to think there's some sort of final 1 beyond infinity. Let's write that down as 0.0 repeating 1. Of course, if the 0 repeats infinitely, then you never get to the 1, so you might as well leave it off the number. Thus, the difference between 0.9 repeating and 1 is 0. There is no difference. Here's another there's no difference proof. Remember how the next higher natural number after 1 is 2? What's the next higher real number? The game is, for any number you claim is the next real number, I can find one that's even closer to 1. One of the many delightful things about real numbers is that for any two numbers, no matter how close, there's still an infinite amount of numbers between them, and an infinite amount of numbers between those, and so on. There is no next higher real number after 1. Likewise, there's no next lower number. If 0.9 repeating and 1 were different real numbers, there would have to be infinite other real numbers between them. If you can't name a number higher than 0.9 repeating, but lower than 1, it can only be because 0.9 repeating is 1. If you don't like it, well, go to college and learn about hyperreals, or better yet, surreals. That's a system where you can have a number that's infinitely close to 1, but not 1. But even weirder, there's infinity more numbers that are infinitely even closer. Anyway, on to reason number 8, another common proof. Take 0.3 repeating, a repeating decimal equal to 1/3. Multiply it by 3. Obviously, by definition, 3/3 is 1, and 0.3 repeating times 3 is 0.9 repeating, which you might have noticed is also 1. The only assumption here is that 0.3 repeating equals 1/3. Maybe you don't like decimal notation in general, which brings us to reason number 9, this sum of an infinite series thing, 9/10 plus 9/100 plus 9,000. And we can sum this series and get 1, but I can see why you might be unhappy with this. It recalls Zeno's paradoxes. How can you get across a room when first you have to walk halfway, and then half of that, and so on? Or how can you shoot an arrow into a target when first it needs to go halfway, but before it can get halfway, it needs to go half of halfway, and before that half of halfway, and half of halfway, and so on. Therefore, it can never start to move at all. Anyway, it's a half plus a fourth plus an eighth, ... to get 1. Each time you fall short of 1, so how can you ever do anything? Luckily, infinity's got our backs. I mean, that's like the definition of infinity. A number so large you can never get there, no matter how many steps you do, no matter how high you count. This way of writing numbers with this ... business, or with a bar over the repeating part, is a shorthand for an infinite series, whether it be 9/10 plus 9/100 and so on to get 1, or 3/10 plus 3/100 and so on to get 1/3. No matter how many 3's you write down, it will always be less than 1/3, but it will also always be less than infinity 3's. Infinity is what gets us there when no real number can. The binary equivalent of 0.9 repeating is 0.1 repeating. That's exactly 1/2 plus 1/4 plus an eighth and so on. That's how we know a ... half note equals a whole note. The ultimate reason that 0.9 repeating equals 1 is because it works. It's consistent, just like 1 plus 1 equals 2 is consistent, and just like 1 divided by 0 equals infinity isn't. Mathematics is about making up rules and seeing what happens, and it takes great creativity to come up with good rules. The only difference between mathematics and art is that if you don't follow your invented rules precisely in mathematics, people have a tendency to tell you you're wrong. Some rules give you elementary algebra and real numbers, and these rules can't tell the difference between 0.9 repeating and 1, just like they can't tell the difference between 0.5 and a half, or between 0 and -0. I hope you see now that the view that 9.9 repeating does not equal 10 is simply un-9.9 repeatingable. If you started this video thinking, I have 7.9 repeating, that 7.9 repeating is 8, I hope now you're thinking, oh sweet, 4.9 repeating is 5, hi, 4.9 repeating. If you're having math problems, I feel bad for you, son. I got 98.9 repeating problems, but 0.9 repeating is 1. Here's the moral of the story. The idea of a number infinitely close to, but less than 1 is not stupid or wrong, but wonderful and beautiful and interesting. The true mathematician takes "you can't do that" as a challenge. If someone tells you you can't subtract a bigger number from a smaller number, just invent negative numbers. If someone tells you you can't multiply a number by itself to get a negative number, then invent imaginary numbers. If someone tells you you can't multiply two non-zero numbers together to get 0, or raise one non-zero number to the power of another and get 0, you should probably say, I'll do both at once, and in 8 dimensions. And if you ignore them telling you that numbers aren't 8-dimensional and that inventing fake numbers is a useless waste of time, and actually try to figure it out, next thing you know, you've got split octonions, which besides being super awesome, just happen to be the perfect way to describe the wave equation of electrons and stuff.